evaluating using the formulas, and then we've done a lot of like proving. Okay. We haven't done as much solving. In each section, maybe one little solving problem where we just kind of used like what we think and how it should turn out to figure it out. But today's focus is going to be strictly solving, but we're still going to need to use some of these tools to help manipulate the problem to make it solvable. Okay. So there's a lot of try these in this section so that you guys can try them. But my preference is that I'm going to go through all the examples first so we can kind of get exposure to different techniques that might help us solve the problem. Okay? All right. So first one that's up here, sine squared x plus cosine 2x minus cosine x equals 0. And we are supposed to find the angle x that makes this true between 0 and 360. Do you see why this wouldn't be one that we did before? Like, oh, just think about the unit circle. What angle makes that true? Like, I don't know. I have to find the sine, square it, the cosine of double the angle, minus the cosine of the angle, and that's all supposed to turn out to be 0. That would be a little difficult for me to just reason through, because it's not like when is the cosine equal to the sine, or when is the cosine equal to the opposite of the cosine. It's not something simple. So what I'm going to try and do is manipulate the left-hand side of that equation so I can get it as simple as possible, and then find out when that equals 0 when I'm at a place that's, like, doable. So a couple of things when it equals 0. Either I can manipulate the left side to get it all boiled down to, like, one trig function, and I can find out when that one trig function equals 0 by thinking about locations on the unit circle. Option number 2, that can't happen, okay? But if you remember our zero product property, we used it a lot with quadratics, it was nice to have something equal to 0, not because we knew when x squared plus 2x plus 1 equaled 0, but then we could factor it, and each factor was much smaller and could be set equal to 0, and those were much simpler to solve. So that's another idea or strategy that we might be using. Matt?
So could you change like cosine of 2x
Uh-huh.
to 1 minus 2 sine squared?
Sure. All right, so do you guys see Matt's rationale in doing that? This helps us two ways. First of all, this has multiple trig functions, sines and cosines. It still has both. Whatever, I'll deal with that in a minute. But the way that this really helped me is that now at least all the angles are the same. This is all about angle x. One of them is not about angle 2x anymore, because that's a whole different angle and causes a little issue. Okay? So then we can simplify this a little bit. Let's see what we have. We have a 1 sine squared x and minus 2 sine squared x. Ninja? Yeah. This is not going to help us, actually. Did I type this wrong? Will you guys check my identity for cosine 2x? Am I right?
Wait, actually, I think that the second cosine squared x is just cosine.
Oh, it's just cosine x. Thanks, Matt. Okay, that's what I did. I copied wrong. I knew something wasn't working out right. It was gonna look like I verified it. That wasn't what we were trying to do, so I was having a little panic attack. But you guys see that I am just a bad student and copied wrong? Yes? Okay. This is not squared. Thank you, Matt. Okay. All right, so let's talk about what we did and why we did it. So first, Matt got rid of our cosine 2x and made it about something that was just about x, so that all the trig functions had the same angle in them, so then we could try and look for patterns where they could be combined. Okay? Then we combined like terms, okay? And then Min Chao had the idea to change the 1 minus sine squared x into cosine squared x. Okay, now cosine squared x and cosine x aren't the same thing, but if I can get everything down to the same angle with the same trig function, I can now try some of those factoring techniques that we talked about with quadratics. So this is like having x squared minus x equals 0 in quadratic worlds, right? We have the same variable. We have the same, here it's just squared, here it's not. So what I would do is I would look to factor this. Okay? The reason I would look to factor it, I'm trying to get something as simple as possible to determine when it equals a number, because that's when I can look for angles on the unit circle. Cody?
How do you get from sine squared x plus
So the 1 is right there. And then these are like terms because they both have sine squared x. So it's like a positive 1 minus 2 is going to be a negative 1. So that made that term, and then that was just the same. So I just combined those two as like terms. Is that okay? And then the identity said that that could become that. Okay? Julia?
I just have a general question.
Sure.
Solving. So, like, say, when say they ask you to find like a double angle or something with the cosine to move an angle, how would you, when you're plugging in an actual number, when it says like cosine squared of a number, does that mean you're just squaring the cosine?
After the cosine's been calculated,
So just like if you were to do it like
Yeah.
on your calculator, you can do cosine.
Yeah, so the squared here is like the cosine calculation being completely done and having it like outside with parentheses. Yes. Okay? All right, so the way that this helped me, this would have been really hard to solve, right? Because I would have been trying to find different angles on the unit circle that like when I find the cosine of the angle and then when I find the cosine of the angle, square it, and then I subtract the two, it comes out to be 0. That might be a little much for me to just like reason through. But when I factor it, it creates these two much smaller factors. And because they're equal to 0, just like with a quadratic equation, we can use the 0 property and say, the 0 product property and say, if these two things are multiplying to equal 0, then this is going to be true when the first factor is equal to 0 or when the second factor is equal to 0. And these are much simpler things for me to solve. Can I find on the unit circle at which angles the cosine of x would equal 0? I can find angles where the cosine is going to equal 0. I could figure that out. Okay. For this one, I'm just going to add 1 to each side. And then on my unit circle, can I find out where the cosine would be equal to positive 1? Yes. So now what I've done is I've changed it so that I had the same angle, the same trig functions to try and narrow down till I have something that I can reason through while I think about like my unit circle angle locations and their sines and cosines. Allison?
Where did you get the -1 and the cosine of x minus 1?
I factored this. So this is just like having like x squared minus x and factoring an x out of there that would leave x minus 1. But I used cosine of x. Is that all right? Yeah? Okay. So let's think about these positions on the unit circle. Now, we only have to think about once around the unit circle, and we can think about degrees because we have from 0 to 360. Okay? So let's think here. Oops. All right. When does the cosine equal to 0? At which angle locations? Monet? 90 and 270. So this part is going to be true when x is equal to 90 or when it's equal to 270. When is the cosine of x going to be equal to 1? At where? 0. And at 360. Now, do we include both 0 and 360? No, according to the inequality, we can be 0, but we're not going to be 360. That's just helping them not overlap any locations. So this equation is going to be true when x is equal to 0. So I actually have 3 solutions to this problem, okay, that x could be equal to 0 degrees, 90 degrees, and 270 degrees. If I wanted to check my answer, I could go back and literally take 0 degrees and plug it into that very first equation and watch what happens. So when I plug it in right here, what's the sign of 0? 0, and that squared would still be 0. So I have a 0. I'm just going to keep track right here for a minute. Cosine of 2x. Let's say I plug 0 in there. 2 times 0 is 0. What is the cosine of 0? 1. Then the cosine of 0 is 1. And all of this would end up being 0. Does it equal what's on the other side? Yes. Okay? All right? And again, remember we had the places where like you really have to check and then places where like I'm being a good student and checking that my problem is right. Okay? Here is like if you're perfect, your problem's going to be right. But if you want to see if you did it right because you're uncertain, you can go back through and always plug back into the beginning to check. Okay? So we're trying to do like a simplification, which is why we got practice with all those different identities and verifying and stuff like that. But once it's simple, now there's a new additional step to solve the problem. Okay? All right, I'm going to come back to the try these to let you guys try stuff later. Well, let me make sure there's not one that's totally different. That's all right. I can still all right. So this is actually a simple equation, but the way I want us to write the answer is not so simple. Okay? What makes this a simpler equation than something like the problem we just saw? Raven? Yeah, so we can just subtract 1 to both sides, and we have it all really nice and simplified and really easy for us to think about locations that meet that requirement, right? That's okay? Who wants this problem on their test? Everybody? Okay, yeah, that's what I thought. All right, the difference is the way they want the answer. What kind of answer do they want? Radians. And what else? All values. Is there a limited time around the unit circle that I'm looking? No, they want me to express all values. So remember when we were doing our graphing and we were talking about domain and range, and some of us just like wrote out the pattern, but others of us said, oh, it's like everything except for like k pi, where k is. Now we need to actually use that type of reasoning to express all, because all is like a sequence of numbers that has a certain pattern, and we need to identify it. So let's first think about, let's pretend like it's one time around the unit circle, okay? Where are the locations from 0 to 2 pi, since we're in radian world, that have a cosine of -1 pi? And that's it, right? So the answer to this problem, if the range of values was from 0 to 2 pi, would just be pi. Are we all in agreement with that? Okay. But now I need to express this constantly. So, okay, so one answer would be pi. What would the next answer be? 3 pi. And then it would be 5 pi. And then it would be... Okay, so what's happening is I'm starting at pi, and I'm identifying each other answer by going another loop around the circle, right? How far is it around the circle if we're talking radians here? 2 pi. So I want to start at pi, but I want to go around the circle again. Is there any limit on how many times I can go around the circle? No. So this is where like the k or the n or something different comes in. So basically you're telling somebody your answer is pi plus 2 pi any amount of times that you want. But we need it to be whole number times, right? Like 1 time around the circle, 2 times around the circle. Can they go backwards around the circle? Okay, so we don't care if it's negative or positive. We don't care if it's 0, because if it's 0, it will just be this number. But it can't be like a half or anything like that. So what kind of numbers can k be? Cody? Whole numbers? We can expand that set a little bit. Good. Integers. Okay, because integers are all the whole numbers but positive, negative, and 0 included, right? So we just say this is our answer, where k is in the set. This means it's an element of, okay, integers. And yes, the symbol for integers was z because I was already taken by the irrational numbers, okay, in case you remember way back, a little algebra 1 action, okay. Is this okay with everybody? So I identified the location, and then I want to tell them, like, hey, you can go around the circle as many times as you want, forwards, backwards, whatever. And the way I tell them that is around the circle, 2 pi, as many times as you want, k, but k needs to be positive or negative or 0 whole number. So k has to be in the integer. Okay? Is this all right with everybody? So see why I made the equation easy, so we could understand first how to write this new idea of the answer. And so now we'll do all kinds of equations, and then we'll see how to write the answers like this. All right. I actually do want to look at part A of this, okay? So I actually do want to look at the try these for this one. So I'm going to do what Raven did in the last one, write it like this, and I can identify angles that have a cosine of 1, right? Which angles have a cosine of 1? 0, and then 360 or whatever, okay? But in this problem, was theta right here? No, it was 2 theta. So I just want to point this out for future, because you can say, like, oh, I know that this is supposed to happen at 0, okay? But then you have to ask yourself, when does 2 theta equal 0? What would theta equal? 0. In this case, it turns out to be the same. It's not that complicated. Okay? But notice that you guys also said 360 would work, right? Let's look at that same idea if we look at 360. If the 2 theta can be equal to 360, What would the theta be equal to? What would the theta be equal to? 180. And does that make sense? If you plug 180 in right here, because of the 2, does it get turned into 360, and then does it have a cosine that's equal to 1? Yes. So we can solve these the same way, but they take an extra step because that 2 right there is changing it. Think about what the 2 right there did to the graph, right? It was a horizontal compression. So think about the amount of times you would hit the same like maximum 0 or minimum. Your wave would go a little faster, and you'd get through more of them in 2 pi. So 0 works, but also 180 works. So this works, okay? And then it will keep going any of those points, okay? Cody.
Like how you like add 1 to the other side to get cosine 2
Uh-huh.
equals 0. Could you like divide by 2 so then you have cosine theta equals 1/2?
No, because this doesn't say 2 cosine theta. This 2 is inside of the cosine function. It's like taking, if I take log of 2x and I divide by 2, does that 2 cancel that? No, because it's inside of a log function. Okay, so it's like order of operations. You don't know what this is going to do, the log to the 2, so it's not a normal 2 like this. Okay, it's not a factor of just 2. Okay. All right, so solving, but the 2 makes it a little more complicated that we have to analyze a little better, and we find out there's actually these 2 spots it would hit around the circle. So it works at 0 and at 180 and then at 360 and then back. Is that okay with everybody? Now how to write this, okay? We do not write this as 2 separate answers because these answers have a relationship to each other. So instead of me saying, oh yeah, the answer is 0, and then you can go like 2 pi, or you can go like 2 pi the other way, or you can go like 2 pi as many times as you want. So instead of me saying that the answer is this would be like we wrote it for the last problem. 180 is like pi. Those answers are correct, but they're not written in the simplest way. Okay? Helen?
Could you say you can speak as pi without a definition the way you say 0 and 1?
Yes. Okay, so let's talk about what Helen just said. And she made a very important point. This works because these 2 points have the same relationship between them whether you go this way to get from one to the other or this way, and it doesn't matter which one I start at, I can get to the other one by the same amount of space, right? So they are pi radians apart whether I go forwards, backwards, start at the 0, go to the 180, start at the 180, go to the 0. They're the same measurement apart every direction and from any point. Does that make sense? So because they have that in common, I don't have to say start here and go around and name this one differently. I can say you will hit an answer every time you start at one of these points, right? So we'll say 0, and you go this much, okay? You can go that much forwards. You can go backwards. You could start here, okay? You can go 3 of them if you want. Either way, you always end up hitting one of these points. So I say start here, and because it has this relationship between them, you only have to add this much instead of a whole loop around the circle. This statement covers both of those points, and it actually simplifies, because this is a 0, what would we just say our answer is? Pi k. And what is k? K has to be in what number set? Integers. Okay, it still has to be positive, negative, whole numbers, or 0. Okay. So I pointed this one out for 2 reasons. I wanted you to make sure that if it said 2 theta, you didn't always have to use one of the identities, because we could figure this out kind of logically on our own with the double angle, but that you had to be aware of it. And then 2, when things have a relationship between each other, there's a simpler way to write the answers than listing them all out. Sometimes we have to list them all out because they don't have that special relationship, but if they have this special relationship, we can kind of condense the way we're writing the answers. Okay? All right, let's see. Okay. This time we're solving for all values of x, but we get to keep it in degrees instead of radians. But we're probably going to have to use k or n. I don't know what letter your book uses, to be perfectly honest. Don't be afraid if it's k or n or whatever. It can be anything anybody wants. All right, ideas. What are we going to do with this? Convert what? convert that to. Okay, so we have an idea to work with the sine squared x minus 1 to make it a cosine squared x. Now, cosine squared equals 1 minus sine squared. Is that exactly the same as what's up there? No, but what we have up there is like a negative 1 and a positive sine squared. So if I factor a negative out of that, I could get what I wanted, right? So I can do what Grant said, but I can't just put cosine squared x for sine squared x minus 1. What would I have to put? Negative cosine squared x, because it's like the opposite signs of what we saw. And they are both opposite, so it's okay. Yeah. Yep. Either way, we'll end up in about the same situation. Yep. Good. Setting it equal to 0 is a good idea, so I can see how everything works out, and if I have to, I can take out factors and analyze what's going on. So I'm going to bring both terms to the same side. So when I subtract cosine squared x from each side, or would you guys rather me add cosine squared? You guys like that better? Okay. You guys don't like negative things, right? Okay. I get 0 equals 2 cosine squared x. Now, this one I can divide by 2. Remember Cody's idea of dividing by 2? Why is it okay here, but it wasn't okay before when he asked? Yeah, this is a factor of 2. This is not the cosine of 2 with something. This is 2, okay? So I can divide by 2, and I get 0 equals cosine squared x. I can square root both sides. I'm growling, sorry. And I get cosine of x equals 0. Now, if this wasn't 0, what would I have to be really careful of when I square root both sides of an equation? Helen? Good. Positive and negative, which would give me a lot more answer choices. So remember, all these solving things that we've learned from the past, we're using them all with our trig identities here. All right, so where is cosine x equal to 0? Oops. Yeah. Where is cosine x equal to 0? 90 and 270. Okay, now we're writing this for all angles in terms of degrees. So we can't just say 90 and 270. So what can we say? X is equal to 90 plus what, Eric? Good. Plus pi k. All right? So he's telling somebody, your answer, you can start at 90 degrees, and you can go, oh, but not pi. What should I say? 180. Check my. So he's telling someone you can start at 90, and you can add to that any multiples of 180. Remember, that's half circles. So if somebody started at 90 and they went half, sure. If they went a half the other way, yeah, they end up at another answer. Let's say they decided to go 8 halves. Yeah, 1, 2, 3, whatever. They're going to end up at one of those answers. Okay? And then I just have to say that k is an integer. I know you guys think like, Ms. Dahl, you don't have to say that. We all know. We might all know sitting in this room because we're talking about one thing in one context and all of this, but somebody reading our work would not know, so it is important that we write that down to be mathematically correct. Are you sure? Okay. Is this all right with everybody? Okay. So infinitely many answers, but expressed in the simplest way possible. Okay. Yeah. Yeah, for the most part, we're going to try and write it so that it's like that. Yeah. And the reason that most of the time it's an integer is because we're always trying to move a certain amount of times around the circle or a certain amount of half circles. We don't want to move like half of a half circle or something like that. We want to just say, oh, you want to move a half circle. So most of the time for us, k is going to come up as an integer in this context. All right. Oh. We don't have to write infinitely many answers this time. We just have to go from 0 to 2 pi. Do you like that 0 pi notation? I don't know if I accidentally typed that or I copied it from the books, problems like that. That's interesting. Okay. So you look at this. I don't know off the top of my head, but what do you want to do to that left side? What's that? Subtract what out? Yeah. What's that? Don't do it. Helen? case. But if we factor out sine theta, it only factors out of the first two terms. But factoring is actually a big key here. Monet? We could add to and then factor, but then the factoring doesn't help us because factoring only helps us when we can use the zero product property. Like if two things equal 2, we don't say like, oh, this one equals 2 or this one equals 2. It only works for the number 0. Eric? But then it would leave us 3 halves in the middle. We can actually just factor it just the way it is. Okay? This is just a polynomial in disguise, and instead of x, somebody has put sine theta in its place. If I had given you this, I bet you guys would have solved it in 1 second. Let me rewrite this problem in a simpler way. I just replaced every sine theta with x. How would you solve that problem? Okay, yeah, so right away you're factoring, right? So something times something. We can do the same thing. Exactly how we would factor this is how we're going to factor that polynomial. There's just not an x in it. Instead of x, what's there? Sine theta. So how did my mind recognize that? Look at the pattern. Same angle, same trig function, squared, not squared, constant, right? Squared, not squared, constant. It follows the pattern of a quadratic. It is a quadratic, just not with x. Okay? So this would factor as 2x, x, 4, 1, fifths. Okay? So however you factor, that's what you want to do. And I'm going to factor this one the same way, but instead of x, I have sine thetas. Now this factoring is useful because it's still set equal to 0. So I'll use my zero product property that says that means this factor can equal 0. Or this factor can equal 0. And now each of those are pretty nice because they have one trig function in them with one angle, and I'm just going to isolate that trig function. So this one's going to say sine theta should equal -1/2. And this one's going to say sine theta should equal 2. Yes? Yes. So this, not possible. Okay. What's the maximum value sine theta could reach? 1. Okay. We know that from our graphs. We know that from the values on the unit circle and from understanding in a triangle that it's opposite over hypotenuse, and hypotenuse is the largest. So 1 is the maximum value we could reach. So we're just dealing with this. So where are the locations where the sine of theta equals -1/2? So 210. So right down here, 210. And 300. 330. Okay. All right. Now, we don't have to write this as like every possible answer. We just have to pick from 0 to 2 pi. So I'm going to write them in radians instead. But one small note, if these were our two angles, we could not write these if we were trying to write like the width plus k pi, like all that kind of stuff. We couldn't write them as one answer because these two angles do not have a consistent relationship. For me to get from here to there is a lot farther than the distance from here to there. Okay? So that wouldn't work to write. I'd have to write two separate answers for this, just making a note about those previous cases. In this problem, we literally just have to list the two angles from 0 to 2 pi, but we have to list them in radians. So theta can equal this. What is 210 in radians? 30 degrees are sixths, right? This is 6 pi over 6, and one right after it is 7 pi over 6. And this one is right before 2 pi, which is like 12 pi over 6, which makes it 11 pi over 6. Okay. And those are my two solutions. Yes, Jenny?
I'm a bit confused on why 210 sine only exists from 0 to 2.
That's if we're using the inverse sine to solve it and using those parameters. This specifically tells us to pick angles between 0 and 2 pi, so we're letting those directions override what we would normally do. Okay? So if someone writes this, we say -30 because this notation has exactly that restriction on it that you just talked about. When someone gives me a problem like this, okay, and tells me specifics about where to look for theta, I follow their directions instead of this. If they gave me no directions, I would follow the directions you just talked about. Is that okay, Jenny? So just a matter of what they say to do, okay? All right. Back. Yeah. Okay. Think. All right, so what would you guys like to do? I'm going to pause the video. I'm going to let you guys work with your group for a couple minutes. So you said subtract sine from both sides. So you had...
So you have 1 and minus sine. And
Okay.
then we rearranged it so it would be 1 minus sine x plus cosine x.
Okay.
And 1 minus sine x is cosine x.
No. Okay. So this is a big thing that we have to talk about. So let's go back to Pythagorean theorem, right? A squared plus b squared equals c squared in geometry. A 3, 4, 5 triangle is a right triangle because it fits this mold, okay? However, does that mean that A plus B is the same thing as C? No. For example, 3 plus 4 does not equal 5, okay? Because the order of operations here is something different than if you just take the radical off of everything. All right. So let's try the other option. Yes.
So you said both sides are equal to each other.
Yes.
Okay.
So it is okay to square both sides. So we're going to go with that idea because everybody else had their hands up and start with that. So if we square both sides, totally okay in this case because are we trying to prove that these two things are equal to each other? No. This is an equation. They are equal. We are trying to find the angles that will make it true. So the purpose in squaring both sides is so we can do exactly what Eric pointed out that we wanted to do. We just couldn't do it that way, but we might be able to do it if we square both sides because then we actually have those things we can substitute in. So sine squared x equals, Monet, I think you brought, never mind. Okay, then when I square 1 plus cosine x, be really careful. Is that just 1 plus cosine squared x? No. Okay. It's 1 plus 2 cosine x plus cosine squared x. Okay, now you might look at this and be like, no, you just made a bigger mess. But we didn't. There's actually something good going on here. Shannon? Good. Oops. Don't know what's going on there. All right. So why would we think to do this? For the people out there that are like, yeah, I'm going to know to do that. Okay. Someone else that understands why Shannon made that decision, what would prompt her to do that? Helen?
Well, cosine squared x, you can subtract like 1 minus cosine x and put it into the quadratic equation you have and you have a solution.
Good. So even though every problem is different here, there are some themes that we can grasp onto. One theme is we want all the angles to be the same. We don't want 2 x's and x over 2's and x's. We just want them all to be x or something like that, right? Or all 2x. Just something where all the angles are the same. Secondly, we want to get the trig function to be the same too, because then we can do things like use quadratic methods and all of that. As long as it's like all sines and all cosines, we can look for things that combine like terms or factor. And if they're not, then we wouldn't be able to do that. So I'm going to go ahead and move both of these terms to this side. So I get 0 equals, that's 0. I get 2 cosine x plus 2 cosine squared x. All right, that's good. Okay, this is good. It's gotten a lot simpler. I have all cosines. It's okay that one's squared and one's not because I have factoring as a tool that I know I can use as long as I'm equal to 0, and I am equal to 0. Okay? So what do you guys want to do next? Factor it? Sure. So we can take out a 2 and a cosine x from each term, leaving us with 1 plus cosine x after we undistribute that or factor it out. And this is exactly what we want. This is now a solvable problem. I have 2 factors, factor number 1, factor number 2, set equal to 0, so I can use that 0 product property and try to solve. So I'm going to look for angles that make this equation true, as well as angles that make this equation true. Okay? meaning I'm looking for angles where, if I divide both sides by 2 here, the cosine of x equals 0. And here, if I subtract 1 from both sides, the cosine of x equals negative 1. Okay. So cosine of x equals 0, and we're just looking from 0 to 360. So the cosine of x will equal 0 at 90 and at 270. The cosine of x will equal negative 1 at 180. Okay. So x can equal 90, 180, or 270. Those are all solutions that would make this equation true. So if I plugged in any of those values for x back at the beginning and calculated the sine on the left side, it would be equal to 1 plus the cosine on the right side. Okay? If you're uncertain about your answer, you could always go back in and check. Okay? All right, any questions about this? I think this is the last one. Yeah. Okay, so what I'm going to do is put up some of the try these so that you guys can try them. Okay, before you guys start trying them, we'll take a little vote, though, about when you want your